Welcome back to another episode of Adventures in Machine Learning. I'm one of your hosts, Michael Burke, and I do machine learning and data engineering at Databricks. And I'm joined by my wonderful co-host,
a very sick Ben Wilson, and I try to manage release schedules for MLflow.
Awesome. So today we are going to be talking about MLOps, specifically the basics. What are the things that you should implement when you're starting out? What are the core concepts? What are the buzzwords? What is hype? What is real? And in this scenario, we're going to be talking through a real world use case that I'm actually working with at Databricks. Unfortunately, we have to keep the names anonymous, but the use case is real and it's pretty cool. So without further ado, I will set us up. And hopefully Ben will have some hot takes per usual. So in this scenario, we are building a computer vision pipeline. We are looking to detect fishing boats at the mouth of a port. And the reason that we're looking to do that is to determine basically how many fishing boats are going in, how many fishing boats are going out, and then we're going to optimize our traffic schedule for those fishing boats so that there's the least amount of traffic, least amount of pollution, and also we just like information. We like collecting data. So it's sort of object detection. We might have tracking. We might have speed involved as well. And the information that we are getting will inform optimization. So what does this pipeline look like? Well, we have cameras hooked up to, let's say, 50 ports around the world, and they're bird's eye view where we have every 5 minutes, there is a little burst of images, or let's actually call it every 1 minute. There's a burst of 10 sequential images every second. So we're minimizing data volume while still collecting representative information about our port. From this, it enters a cloud storage location. If you're in Azure, we'll call it ADLS. If you're in AWS, we'll call it S3. It doesn't really matter. It's entering into a key value store that is easily accessible from your compute platform. From there, we do a little pre-processing, clean up the data, remove images that are just not readable, and then we throw a computer vision model at it, do some post-processing to make the predictions into a usable format, and then use that to inform business decisions. So let's say we have the very most bare bones implementation of this pipeline. It's Python code. It's not unit tested. Our CV model is crap, and we don't even know how to evaluate it or even serve it or even think about serving it. So let's start talking about the MLOps use cases here, Ben. Prior to actually building out improvements to this, we typically want to do some requirement scoping and gather what is necessary for this business. So what are some questions you would look to ask or at least think about when scoping a requirement like this?
Like the number one thing that I ask for implementation complexity is going to be after the model predicts whatever it's going to predict or infers whatever it's going to infer. How long before either a system or a human can take action on that?
Okay. So let's say that for simplicity, and again, I've seen this use case a lot throughout Databricks field engineering, that there's a lot of low latency use cases, but typically decisions are not necessarily, they don't need to be real time. So if you have sort of a batch process with low latency or with high latency, that's fine. So in our example, let's say every week we will publish a report to subscribing organizations that will say, all right, this is how many boats went in this day. This is how many boats went out this day. And then this is the optimal traffic configuration for that port that you guys should implement going forward, or something of that nature. But let's say we have a weekly frequency.
Yeah, that makes it cheap. There's also additional questions for this particular use case that I would start asking, which is things about the use case and the output data that comes out, or the output data that could be coming out of this solution. Is it ever going to be used for something else? And what I mean by that is, like, we're taking pictures of a harbor. Are we ever going to change the frequency of those images? And are we ever going to try to do something clever with those images? Stuff like we have cameras pointing in two separate directions, and we have timestamps associated with them. Can we use computer vision to read the whole number of a ship? So we'll have, you know, on the green light and the red light of the harbor, for anybody who are not mariners uh, or ex-mariners, uh, port entries are it's kind of like the highway in and out of a port. Green light on one side, red light on the other, and you stay in your lane so you don't
Planes
hit
have
another
this
boat.
too. Fun fact.
Yes, they're sticking up out of the water, just as navigation aids. Um, so you would want to point in, 4 directions if you're going to do something like this. And can you determine things from that to say, okay, boat A1 left at 4 a.m., out of the harbor, comes back 5 a.m. the next day. Can we determine the draft of the boat from the images? Turns out, yeah, you can. And that can be correlated to the amount of cargo they're now holding, unless they have filled their ballast tanks and done something crazy. But generally speaking, you don't do stuff like that. So if there's action that needs to be taken in the future from data that you can glean from that, like, is this going to be forwarded to a port authority somewhere? It's going to say, hey, you need to inspect this boat because it's super suspect. Like, only, like, nobody's supposed to fish more than 5 tons of fish with this type of boat. And based on the draft measurement of this ship, it looks like they're holding 40 tons. So send somebody out to inspect. So once you get the answer with something like that, if the customer that you're working with is like, no, we're never going to do something like that, we have zero interest, then move on, continue with something simple. But if they're like, actually, that's a fascinating idea, maybe we should think about that, then that now becomes a like, not a must-have requirement that you're going to put into your design. It's a could have, and that informs your design process to say, we don't have to do this right now, but we shouldn't make decisions that make doing this completely impossible in the future without a complete rewrite of everything.
Yeah. Yeah. Designing for something specific is really important, but also designing for the nice to haves and the could haves and making your code modular for those potential improvements. It's really, really valuable. And it typically isn't that much work because they're nice to haves. If it adds a lot of complexity, you won't implement that additional feature. But if it's simple, it's sometimes just like add another downstream use case with another column in our prediction set. If it's that easy, I mean, I don't see why not. So yeah, designing for the nice to haves is really valuable.
I mean,
So
this would be an architecture decision as well, because we're now talking
mhm,
about, well, if we need to take immediate action within 20 minutes of this picture being taken, we're now talking about, we can't schedule this as like a cron job. It now has to be active online, and there's costs associated with that. So that's not something for the data scientist or the software engineer or anybody involved in writing the code to determine. It's their job to write that down and say, we need a decision to be made on this. And then you go have the business people, or you know the director of this nonprofit organization. They're going to make the call, like, yeah, that's valuable, and here's how we're going to fund that. Or they're going to say, that's awesome, but we don't have money for that, so we can't do that.
right. Okay, cool. So in our scenario, we've gathered some requirements about the purpose of the data and specifically the latency and how incoming data will be processed into model predictions, which is processed into decisions. So now let's get into the fun part. We have the use case. We're going to throw some buzzwords out there, and I'm curious what you think about these buzzwords and what infrastructure, specifically from an MVP perspective or a minimum viable product, should be associated with those buzzwords. So, first things first, something that I am very fond of, EDA or exploratory data analysis. How do you go about building infrastructure for that?
So for this use case, the EDA is going to be what I would call prototyping phase for what I do now. We build a prototype when we do a design, and we want to try to explore all of the the things that are going to bite us during development time, or theoretically when we ship to production, we want to know beforehand to know what the risks are. And what I would want from a system like this is, you mentioned pre-processing of image data. That's a pretty critical thing. Like, you need to make sure that the data going into that model is going to be useful to that model, even though we haven't built the model yet. We need to make sure that we're generating data that is meaningful. So while we're doing prototyping, we would be looking at, okay, can we get the data from object store in a timely manner? Okay, what tool are we going to use to read that into, some sort of tensor relation data? What are we going to use before that, before we convert it to a tensor? We're dealing with just RGB color space volume for this image. We're probably using something like OpenCV. It's pretty standard in Python. There's tons of other vision packages that are out there, but we'd probably want to stick with something that has a lot of documentation. Not looking for the latest and greatest, coolest new tool that's out there. It's got 15 stars on GitHub, and yeah, it's really active. Well, when was it first uploaded? A month ago? Maybe pass on that one, or test it out, see what you like and what you don't like about it, but have a fallback that allows people to play around with that. And for the EDA aspect, what I would be looking at is starting with a very simple interface to allow us to visualize images that are stored on object store, and then be able to provide very basic APIs that would execute some sort of processing data. At first, that's just going to be input output, right? We're not going to be doing anything to the image. We just want an API that will allow us to read an image and then return that image, so that we start thinking about, when we start doing this processing logic, we'll probably want to create some sort of modular design that allows us to execute different manipulations of the image. And you don't have to decide what your actual code design is up front, but it's good to have something in place that allows you to know, like, okay, this is going to be an API that we're going to create that does this. And it does it pretty well. It handles authentication for us to access the image, and it executes some arbitrary processing code. And we get returned an image that can be displayed on the screen, so we can see the picture of it.
Right.
So yeah, that's what I'd be thinking of, and how to make that as simple as possible and as extensible as possible.
Yeah. So tangibly, if you're the TL for your team or even just designing some of this architecture, the core things for EDA is you need to access the data. So creating some helper functions that auth and then query from whatever storage you have. That's super important. And ideally, that's a shared module throughout your team. The second is it needs to run somewhere. So whether that's on your laptop on an IDE, whether that's in a notebook environment in the cloud, or whether you're even like converting from your IDE into the cloud and then pulling those responses, uh, you need some way to test and run things. And then finally, it'd be nice if there's some sort of standard packages that facilitate your EDA process. So for CV, it's sort of a niche area of ML because it's so different from supervised and unsupervised learning in other areas. And there are lots of great SaaS products, but also open source tools that will display an image, highlight interesting things. So those three components are very important for EDA. Sound about right?
Yep. The pillow package will be your friend.
Yeah. Cool. Another buzzword. I've heard people talk about this so much, and I was wondering if you could explain what ETL means.
Extract, transform, load. Um, that means you're loading data from some raw source. In this case, it would be just images stored on object store. Um, and it's kind of a loaded word. A lot of people just throw it out there like, oh, let's just ETL this. It's like, well, what are we talking about here? ETL incorporates a lot of different concepts into it, but at its very highest point, we have some sort of system architecture where we're talking about, how are we storing data? How are we accessing it? What operations are we doing onto it? in order to get it into a usable form. That's really the big overarching theme of that. And then incorporated in that are what languages, platforms, tooling, systems that you're using to do all of those things. So ETL could be, hey, we're storing our data in object store. Cool. Are we organizing that in a way that makes our downstream use cases easier? Like model training, model retraining, inference. Are we doing this in a way that we can apply labels to the data or apply metadata to it in a stored format? And those are all things to think about that are about like not just the project that you're immediately working on, but other projects you might work on. So it might be staged ETL, like, hey, we're taking it from just raw, unfiltered images that are being taken and uploaded to this thing by an automated system. And then we have the need for a sanitized image format that has, EXIF data or metadata that's been pulled out of that actual image and stored as metadata along with this file, or stored in a table somewhere that we can say, here's our inventory of files that have come in. And we know like, that's in our index, basically. Or is it, this is the only use case that we have for these images, so we can do additional processing to prepare it for consumption later on? It's all just questions that need to be answered by the engineering team. So like, what do we need to do with this data?
Right. And to maybe add some underlying themes to this ETL conversation, typically there's a pre-processing step, so source to model, and then a post-processing step, which is model to decision making. And within the model development process, typically you can break it into 3 steps. So initial model development, model training, and then model inference. For EDA or initial model development, you typically want to expose a lot of the raw data to the users, whether it's in a clean format or just simply the raw images themselves. And then for model training and model inference, those typically are more tightly coupled and more robust sets of code. So for EDA, you'll just play around. For training, you want your code to be working consistently. And then for inference, you want your code to be working even more consistently. Training theoretically only has to work correctly once, although it should work many times. And then inference has to work in a scheduled fashion. So when you're going about developing these ETL frameworks, um, it's really not that complex in terms of the high level concepts. It's going and getting into the nitty gritty of should this column have this value, ensuring data quality, data munging, all these feature transformations and feature engineering. That's actually the challenging step. But for CV, it's a little bit easier. That sound about right?
There's a lot of stuff that you end up doing in supervised learning, I think, that is very different than what you would do for image classification. But depending on what model engine will be used for the object detection, whether it be a deep learning framework or classical OpenCV, um, that feature transformation step could be super simple. Like, hey, just filter out garbage data. If there's no resolution available in the file, like it's just a completely white image or completely black image, and there's no contrast. Yeah, don't use that for training. Or do use it and label it as bogus so that the model can detect that, like, hey, this is invalid. So that when you're doing online inference or batch inference, you can basically get that labeled as unrecognizable or something. So you don't have data that comes out of that. But if you're doing classical stuff, which arguably is more accurate, depending on how much time and effort you put into it, that could be orders of magnitude more complex than any feature engineering you'll ever do for supervised learning. So we're talking about color space theory, transformations, manipulations of images, where we're correcting for chromatic aberrations. We're detecting things like lens flare and removing that from an image. Uh, there's some pretty advanced stuff that you can do with image data in order to clean it up so that you're not getting a whole bunch of false positives or false negatives.
Got it. Yeah. Okay. Well, I'll revise my statement a little. It might not be It's just different. It depends upon your use cases. Yeah. So for model training, what do you think about in terms of model training for the minimum viable product stack? And actually, let's elaborate a bit. Let's say we're using a base model and we're fine tuning in this use case.
I mean, I'm assuming you're talking about deep learning. So that's probably the first thing that I would try because it's fast. Somebody else has already done all the work to get this neural network to understand the concept of what shapes are and how to follow a line in a convolutional, you know, collection of images. So yeah, I'd start with that. Some pre-trained model that's out there, and then fine tune it on the data and just see what happens. And that's a lot of work, particularly with images. And I think a lot of people that get into this don't realize, and people that are getting into stuff like LLMs now, they don't fully appreciate the monumental mountain of work involved in validating your hypotheses. So when you do this image classification thing, like detecting fishing boats, you're going to have to get a whole bunch of data, thousands and thousands of images of these port events. And you're going to have to make sure that you have representative samples at different times of the day and night from each of these camera locations that you've installed, and then a whole bunch of other random ocean and boat related imagery. Because you want to be able to basically teach this thing to determine, is that a fishing boat, or is it a cargo boat, or is it a sailboat, or is it a tugboat, or is it a pleasure craft, is it a yacht?
How many boats can you name right now?
Too many, man. And you want to take some abnormal things that might happen as well. So get pictures of people in a canoe, people in a kayak, get a picture of somebody swimming, get pictures of dolphins, whales, whatever, anything that could potentially be at the entry point. Somebody moving barges on a river or something. You want these labeled images to be something that could theoretically have somewhat of a probability of being present in an image, so that, like, if that's not in your training data and it's not labeled correctly, if it sees that in the future, it'll probably mislabel it as something that's not correct. And then you'll be like, wow, the model sucks. Like, no, your training data sucks because it didn't include that. So there's a lot of work involved in that. It's a lot of creative work, in my opinion, of selecting an appropriate training set to make sure that it can detect false, like, get your highest ROC curve on classification. But
Yeah.
then on top of going through and doing all of that, you then have to run these images through this model and look at the output. There's no algorithm that you're going to use. You can calculate ROC curves, you can calculate accuracy percentages and these metrics, but when you're really digging in and seeing, like, well, this model was 5% lower than this other model, just seeing the numbers on a screen, it means nothing. Particularly with this, like with anything, any supervised learning. Experienced data scientist is going to say, okay, I want to know why. Like, what is it getting wrong? What is it getting right? Are there patterns here? So you start creating like a massive spreadsheet and getting the instances of images that have been misclassified, and then using the human brain to figure out, okay, why is it getting this? Okay, I'm going to create 5 hypotheses. I'm going to test all of them. Do I need more training label data here? Do I need more examples of this particular image at different times of the day? Can I simulate that? Can I just darken the image? Can I start changing colors around the image, like changing the color of the water? You can do that with tools like OpenCV. You can detect the color space range and then change the blue water to green water, change it to red water. Because, by the way, that does happen. Clay and both, algae blooms can happen. You really don't want that fine-tuned model to start associating a fishing boat or not a fishing boat with a particular color of the water. Because if
Right.
that is a high correlation in all of those images, like fishing boats leave in the morning to go do fishing, is the water always just dark at that time? Well, now it's going to start, if it's unsure, that's the larger area in the image, and it's going to start associating that. So these are things that you have to think about while doing that evaluation.
How do you go about most efficiently building a representative training set?
You take the data that you have, try it on whatever you think is the most viable thing to test out first, and then do the process that I just said. Like, use the evidence that's presented to you to determine where is it getting confused, and then try to figure out why it's getting confused. And then you run a bunch of tests. Say like, hey, seems like time of days might be a factor. Let me get a bunch of images from the internet um, of fishing boats near harbors that are coming in at 4 p.m. in the summer in the northern hemisphere. Maybe there's other factors. Um, you want to be sure to have enough representative samples of different permutations of elements within the images that it can isolate truly what we are able to do very trivially with a little bit of training. It would take a human a couple of weeks to learn to identify fishing boats in pictures, and versus any other type of boat. Look through a couple 100,000 of them, you'll be able to pick out the fishing boats in any image. And our brains are designed to do that. These models aren't, but they can be trained to do that with enough, positive and negative examples.
But diving a little bit deeper, so I am, let's say, a very lazy data scientist, or I just really value my time and don't want to do extra work. Um, are there any sort of shortcuts first? And then second, what's your stopping criteria for my data is representative enough to stop and just have this model be in production? How would you go about thinking about that specifically for this use case?
I don't know. I've never thought of that, actually, of how can I half-ass a model to like deployment for something that's production.
Well, that's a strong word, but how can you, if we're thinking about it like a search algorithm, we're searching through a possible space of all of the images in the world, all of the labels of the images in the world. Obviously, we can't do that.
No,
So, how do we incrementally reach a good enough point? Like, what are the tricks and hacks that you can think of?
I mean, stuff that I've done in the past is just reuse my own training data, but manipulate the image. So darken it, change the contrast, change it into
Nice.
black and white, rotate the image, do all sorts of crazy, stupid things. Sometimes that stuff works. Sometimes it's now going to start learning other patterns that you didn't want it to learn. That's always the first step, is use your own data, but you also have to analyze your data when you notice there's discrepancies. So maybe it's always getting it wrong in this one harbor. It's always misclassifying the boats. Well, is it because fishing boats in that part of the world are fundamentally different looking than any other part of the world? Or is it because they're all painted a certain way because of some cultural reason? There's tons of reasons that it could, like paint, like hull painting is a good example. What if in the rest of the world, fishing boats are all just random colors, but in 3 parts of the world, military vessels are always black. So like harbor operations, port operations type stuff. They're tugboats, they're close inshore ships are all black, like jet black. They have guns and stuff on them too, but they're a boat. And what if this one location in the world, uh, this one harbor, there's a monopoly on the fishing fleet, and it just so happens that the company that or the family that has this monopoly in this area, they really love black fishing boats. Starts getting classified completely as military vessels. So do you need to provide additional data or additional examples to contravene this? And how do you handle that?
Yeah.
That's probably not something that you're gonna just cleverly say like, oh well, if I change the contrast or go black and white on my images, it'll all of a sudden start working better. Because then you start after thinking about at inference time, you now need a pipeline that says classify as color space, and then another one that says classify as black and white, and then look at some sort of probability ratio on those two outputs. So there's lots of nuance to that to get it to solve that problem. That's why training, like fine-tuned training, it seems like it's always going to be easy. The devil's always in the details with your feature data.
Right. And it sounds like subject matter expertise is sort of the linchpin of doing this effectively. Like the red and green example, if we're trying to determine fishing boat direction, that is about as strong of a signal as you can have. And if there's no red or green light, then default to whatever your backup plan is. But red or green is a universal definition of to determine what direction the boat is going. So leveraging things like that is very effective.
Yeah, and having metadata associated with where that particular boat came from or that image came from to be able to feed in with it as well, if at all possible, or use it to decorate the output that comes is
Right.
also super critical.
Yeah.
Now, that would be another ETL job, but that would be like a one-time thing or very infrequent where you're saying, here's our master index of each camera ID, and this is the direction that it's pointing in, and you now have some other fun stuff to think about, like how do we make sure that over time the cameras aren't readjusted? Do we get a
Yeah.
different perspective or different zoom? Or what happens when we upgrade the camera from 1080p to 4K? Is
Got
there
it.
some, we need to know when that happens, and we want that to be automated. We don't want to find out about it 2 months after the model starts falling apart and be like, oh, this all of a sudden sucks because somebody ran into our camera and now it's just pointing directly at at the waves. So you need something to say like, I have I have some sort of uh, alignment in the image, some feature like, hey, there's a lighthouse in the background or there's a building. I need to use OpenCV to say, is this element within 10% of this range of the image? Do I have this addressing mark? And if I don't, fire an alert. And that would be part of like pre-processing to say like, hey, data from camera 173 doesn't look right.
Yeah. Okay, cool. So that's an aspect of model training if you're looking to do an MVP scenario. Yeah, think about curating your data set. That's always necessary and formatting your data in the correct way. But Ben, so I was reading about this weird thing called model versioning, and I was wondering if you could explain why would we have multiple versions of the same model?
That's a temporal thing. So like a lot of people who are starting on a project like this, and maybe it's one of their first, or maybe their first 10, or even first 50 ML projects that they've worked on. Sometimes you don't think about what's the after story. Like we build the model, we do all the validation, everybody's super happy, it's working great. What happens when it falls apart? What happens when that fishing fleet in some river mouth at a port in Malaysia, it's now they now no longer like black fishing boats, they like green fishing boats, and they repainted their entire fleet, and now it's not picking them up at all because it's not looking at the characteristics specifically of a fishing boat from that part of the world. It was looking for black boats in that part of the world, like with other features that are in that fixed camera position. So when stuff like that happens, you need to retrain. So you need to take older data along with all that new data and get enough of that new data so that you have enough in order to do that and retrain the model. And then you save it, you log it. Should use MLflow. It's great for this. And then once you have that and you validated it and you know that, hey, it seems to be working better on our holdout validation data than our old one. And we went through and checked all of those scenarios where this was not working so well on version 1. But on version 2, we validated like, yeah, it's classifying these correctly. We think we're onto something here. And the metrics don't show a degradation in any of the other regions of classification. So maybe we're at a 93% accuracy or something. And in all other regions, we're at 93.8 versus 93 before. Great. But in that one region that was at 93% and then dropped to 2%, we're now up to 93.8%. Then, okay, that's version 2. Deploy it and then monitor it.
Right. Okay, so it helps us sort of track how a model evolves over time. And one of the things that Ben hinted at is if something breaks, you can revert quite easily. And also, if you want to sort of track the progress of the development cycle of this product, it's really helpful to do diffs on model versions, just like with model code. Did hyperparameters change? Did we add these features? Did this new feature really impact our accuracy? So just having versions over time, it's really cheap to store and it's also really valuable. Now, there's this other buzzword. I just love buzzwords apparently. It's something like CI/CD. What does that mean?
It's a loaded term. So continuous integration, continuous deployment is what it stands for. And to somebody who does what I do now, that term means something way different than who I was 10 years ago. 10 years ago, that meant I ran through a manual integration test of what I was just talking about. Like, hey, I have these 800 new images that didn't perform so well in the version prior to this. I ran it through, I validated that they're all classifying much better now. Things look good. I save a version of the model, and then I have the script that basically takes that version of the model artifact, sends it to a production system, and then the cron job that's associated with triggering the batch scoring is now using my new version. And it's not like continuous deployment, but there is some amount of automation involved in that with respect to I'm not manually going through the steps of taking that model artifact and copying it over to a production system and then setting up everything again to make sure that it's pointing to this new artifact location. Now, CI to me from 15 years ago meant I could take 100 images, run it through that model, and I get predictions that come out. I'm like, yep, looks good to me. It's classifying. Ship it. CI to me today, it means something completely different. And this is a suite of unit tests that are checking all the functionality within the code that we're writing. It is external to the code itself, has nothing to do with anything that gets deployed, but it's run to make sure that any changes that we're making in this living code base, particularly because there's multiple people working on it, that things that we touch hopefully aren't going to break everything, and that we're not creating a new feature that's fundamentally broken. Now, for the ML side of things, I don't build ML models anymore. I don't do that stuff except for demos. There's components to that are applicable from software engineering, which is all of that feature pre-processing that we were talking about, like manipulating images. What if we need to invert the image or change the color space or filter out bogus stuff from the image or clean it up, like try to increase the resolution or decrease the resolution, whatever we're trying to do. each of those things are some sort of functional application to a data object. It doesn't matter how you write the code. You could put that all in a bunch of classes and modules, or you could write it as a bunch of functions, or it could be a bunch of Python scripts that just get called and do this on an input object. Doesn't matter. It's just whatever you prefer. Because to a computer, it's all the same instruction code set anyway. Things get different when you're moving into building stuff like tooling or libraries. Then how you write your code and what design patterns you use really do mean something. But the vast majority of data scientists out there are not writing code for that, so they don't need to worry about that.
Right.
If you need to do that, go hire some software engineers and have them build it properly, because it's just a different skill set, completely different way of thinking through problems, totally different. So, but the same principle holds for that CI aspect. So before you take your changes that you're writing, some new features as part of this image manipulation, pipeline that you're doing, each one of those operations should be validated. So you have some example image, like save a bunch of your images to your repo, like in the test directory or something, or generate images, like test images, and then run them through this function and make sure that it's doing what you're expecting it to do. Do you have an example of the exact transformation that you want it to do? It should be a deterministic process. So make sure that in calling that function, it's generating the correct manipulation for you every time. And that might sound stupid to a lot of people who are doing like this type of work in ML. They're like, this is so dumb. Like I just wrote it. I know it does what it does. And I just saved the output of this. Of course it's going to do what I just told it to do. Well, a year from now, when you're on version 39 of this model and you've touched that function 17 times, is it still doing what you expect it to do? Is it consistent with what your original idea was for that function? Because if it's not, you're now introducing uncertainty to this model. So it could be learning things or, getting input training feature data, or on inference, even worse, it's getting different inference data than it's ever been trained on. You just need to make sure that you have validation of that. And
Right.
the continuous aspect of that is before you merge into your main branch of a repo, and you should be using a repo for data science work. Before you merge that branch into main, like those unit tests that you've written, whether you're using Python unit test framework, my condolences, or you're using PyTest or some other new fancy thing that somebody's come up with recently. Whatever you're using, wherever it's running, doesn't matter. Could be Jenkins, could be Circle CI, could be GitHub Actions. I'm a big fan of the last one there. It just needs to run all of that stuff. Even if it's something that you're running on your local laptop or running it in your compute platform prior to merge, you need to know that, like, hey, all of these tests, they're green, they're good to go. I'm now secure in knowing that I'm not shipping something totally broken that's going to get me a super nasty phone call at 1 p.m. on a Saturday where I have to come into the office or log in and fix all of this stuff.
Right. Yeah, there's no better feeling than having all your tests pass and knowing that what you just built probably won't break the entire repo. I love that feeling. So that's CI/CD, and then there was one final buzzword that I was reading about on one late afternoon. Model monitoring. Why would I want to monitor my models? I don't like they're working. We unit tested them.
I can't even tell you how many times I've gotten blank stares from people when I've mentioned, like, "Hey, you doing attribution modeling of your model?" They're like, "What do you mean? It's generating predictions." I'm like, "Yeah, we could swap your model out with 2 lines of Python code that says, if this condition return 1, else return 0. That's a model. It's returning data. But if you're not checking to make sure that whatever the reason for this model's existence is, like it's got to interface with something. It's got to be modeling something. That's why we call it a model. Um, whatever its representation is of the true world outside of its compute environment, if you're not taking measurements of that and then attributing its behavior back to the model, you have no clue what the impact of this is. This applies to like the thing that everybody loves, you know, OKRs, right? Key results. The second half of that, of the objectives and key results acronym. Key results when you're planning out work relate to how are we going to do something, how are we going to measure its impact on the business or on our customers or on the industry at large. And there's some metric that you're collecting, and you have to sometimes creatively think about that. So my question to you, Michael, what would we measure for this model?
Oh man, what a good question. So as you were talking, I Googled the different kinds of drift. And I feel like over the past like 15 years, they've been adding types of drift just left and right.
Uh-huh.
But the core concept is the environment that you created the model is different than the environment now. And what that tangibly can mean is your covariates or your predictors have changed in some way. There's a new label, there's a different label, there's a distributional shift. It's just different. Or your inference data uh, is new, and that's typically a very common scenario where, like, let's say you have a tree-based model that doesn't smooth or doesn't use splines to sort of fill in gaps. If a new target or a new y column, a value in that y column is added, your model might freak out and be like, I don't know what that is. um, so there's a lot of different ways that basically your data can change over time. And then also there's a more nuanced thing called conceptual drift, where the assumptions or sort of the environment that like the business environment that you created that model, those assumptions and business environment have changed so that it's no longer uh, relevant to the model that you created. So there are a million different ways to measure data drift. You can just look at distributions in your predictions, distributions in your predictors, and that's a very good start. But thinking critically about what drift actually means, and then creating sort of scheduled checks is how I at least approach it.
Yeah, 100%. For this particular use case, there's a number of things that I would do. Um, First is exactly as you said, distribution. So we're doing statistical process control on a time series to say how many fishing boats are we detecting per camera over time. And we want to alert on the classification changing dramatically. So if we go way up all of a sudden or way down, or we start drifting lower and lower over time or drifting higher and higher over time, it doesn't necessarily mean that our model is malfunctioning. It can mean that the absolute ground truth of what the model is trying to do is accurately reflecting changes in reality. Bonus, cool, it did its job. It's alerting us that something is changing. But if it's changing and reality is not affecting that, our model is no longer capable of keeping up with the new images that are coming in due to a number of different factors. The the action set at that point depends on what project you're working on. So for this one, that would be audit time, everybody's favorite time in machine learning, which is stuff is broken. Everybody on the team, stop what you're doing and pull the last 2 weeks of classified images. We're going to split this up. Everybody gets 1,000. Go through, create a spreadsheet, and tell me if it was right or wrong, and then try to figure out, like, apply a label to each of these right or wrongs and try to group these together into areas of misclassification. That informs our retraining process. We're like, oh, yeah, Indonesia switched all of its fishing boats to green. What the heck? That's weird. We need to retrain for this. Or it could be, huh, this port is now actually sending out 400% more fishing boats every day. What is going on? Maybe we need to inform a government somewhere. They're like, hey, I think they're in violation of some treaty or something. Great, you know. But if it's you don't just look at model drift as like, oh, we detected drift, we just retrain on newest data. That's not going to do anything. It could. You could get lucky and be like, hey, it magically just fixed itself by just us retraining the model. That's happened for me 3 times in hundreds and hundreds of instances where I actually did the lazy thing. And I sometimes I do that just if it not for deep learning, but for something that takes a couple minutes to train. I'll just trigger it again on latest training data, provided we have good labels, see what happens. And that less than 1% of the time, and I look at the results and I'm like, let me audit this real quick. I'm like, wow, that actually did totally fix it. Sweet. The other risk, the other, anything else that I've ever done, it's because there's some fundamental training, like flaw in the training data that's no longer captured. And it needs to be retrained, but there's some actions that I have to take to engineer features to make this more useful or make the model adapt to this. Uh, the worst case scenarios that I've dealt with for these are stuff like fraud detection models. Those are a nightmare. I hate them. I know they're super important, but maintaining those is the worst thing that I've ever done as a data scientist because people are clever. And when they start finding out how they, account number 119 that they created got flagged for this particular action, and it wasn't even able to complete one of its fraudulent transactions, they're going to use their brain pan to come up with some new clever way to scam your company. And then when they figure that out, it's going to proliferate. And now all of a sudden, fraud rate goes up 30%. And you're like, what the heck? The model is not detecting this. Yeah, because it's new and nobody's ever tried this before because humans are creative. And now you have to try to figure out how to detect that in data. And it's just a whack-a-mole game and it sucks. And you're constantly working on feature engineering for those models.
Yeah.
It could happen with the phishing stuff. So if this is something that becomes regulatory and you're looking at draft of the actual ship and like trying to figure out what the hull number is so that you can link it up to a data set that contains the actual owner of that vessel and what their address is so that it can be forwarded on to a government agency. People are going to start getting clever. They're going to start obscuring their hull numbers. They're going to figure out like, well, how did they figure out it was me who pulled too many fish? Well, they probably have cameras set up somewhere. So let's make our boat not look like a fishing boat when it leaves the harbor or when it returns. They start putting cardboard boxes up over, the fishing net booms, or doing something like draping nets over the vessel to make it look like a different type of vessel. So if people find out that you're doing that and that there's some repercussion to the usage of that model, humans will get innovative and they will start doing stuff to try to defeat what you're trying to do.
Yeah, 100%. That would actually be a really interesting use case. Like, do people start painting their boats pink because color is a predictor or whatever it might be?
I mean, if colors are a predictor in your model sucks, like big time.
Heard. Yeah, that's a good point. But yeah, lots of interesting discussions here. And a cool use case that, again, is real world, and hopefully we'll be implementing it at some point soon. So, yeah, that's pretty much it. I'll quickly summarize. Today we talked about sort of the MLOps 101. If you guys are starting off and you have a model use case or even just an initial version of a model pipeline, these are the MLOps practices that will get you the farthest starting from an early stage. So, lots of really good information throughout this, but some things that stuck out to me are when you're scoping, a really, really core concept is thinking about the latency between incoming data and then the use of the model predictions. So that sort of determines your SLA. It's also great to think about if there are other ways that the predictions can be leveraged and specifically additional use cases. So in your training data, is there more information we would like to extract? For EDA, the sort of the core concept is we're looking to reduce the barriers to prototyping and exploration. So creating utils that your team can reuse and compute environments that are interactive and friendly, specifically for CV, really, really important. For training, your data is the core of how good your model is going to be, and your model is only going to be as good as the data. So curate your data carefully, both on the positive and the negative example side. Um, some great tricks in the CV space is manually manipulating the raw images. Another thing that I've seen used a lot is iteratively retraining. So you manually model a subset, then you use or manual label a subset, excuse me, then use the model to label that subset, manually review, retrain, and sort of iteratively do that process. It's a nice little hack. But the key thing is understand the fundamentals of what drives your predictions. Specifically in our fishing boat example, red light, green light, remember it. Then for CI/CD, it's just tests and deployment. It's that simple. If you need a fancy implementation, go ahead, but you simply just want to write code that will validate that your outputs are as expected, and then sort of a containerized environment so that when you press play, you can actually deploy it without doing a pip install manually. Anything else, Ben?
No, it was a pretty good summary.
Cool. All right. Well, until next time, it's been Michael Burke and my co host.
Ben Wilson.
Have a good day, everyone.
We'll catch you next time.